Hi everyone, thank you for tuning in to this version of our bi-weekly video. And I'm so delighted to be here in the basement of Witmer Hall with Professor Markus Allgaier, who is an assistant professor of physics. And Markus, welcome.
Hi.
How are you?
Good, thanks for being here.
Yeah, it's my joy. And we're eager to hear more about what you're doing down here in the basement of Witmer.
Yeah, absolutely.
Yeah, but before we do, tell us a little bit about your background and how you came to UND.
So by training, starting from when I was a PhD student, I dealt with quantum optics. So that is doing optics with very small amounts of light. And that was always with applications in mind for secure communication. So how to use the properties of light when you have very small quantities of them to make telecommunication more secure. And from there, I went on with my career at the University of Oregon, then University of Colorado at Boulder, working in this realm. So it was a welcome transition to get to come here and continue that and work in applications in sensing with light, communication with light, and talking to satellites.
Nice, exciting stuff. And we're glad that you're here at UND. And it's now been 2 years since you first showed up on campus. Yeah, so that's wonderful. And tell us about the research that you're doing in this facility and also as part of your broader portfolio.
Yeah, so the quantum optics are still the main thing. So I know how to make photons, which are the smallest quantities of light with quantum properties, how to manipulate photons, and how to measure photons, and how to push them around a little bit. So we still have research going on making the sources of these photons, so the light sources that we might use for secure communication in the future. We use those photons for taking measurements with light. For example, we have projects where we shoot lasers into snow and ice to measure its properties. And then the big part that's coming up with this facility is to use photons and light to communicate with satellites.
Nice. And why would you want to use lasers to communicate with satellites? There's other ways of doing it, but lasers are somehow more effective.
Yeah, it is harder, but it makes everything better. So up until now, from the space race in the 60s and still now, we're using radio frequency to talk to spacecraft. And there's a whole breadth of that, from literally VHF, what you could do with amateur radio, to very high frequency antennas that are 40 feet diameters and cost tens of millions of dollars to build. And that's the ones that we're using mostly for things like weather satellites now that produce a lot of data. And so there are things about that are easy and things that are hard. The easy things is with those radio waves, when you shoot those into space, it makes a really wide cone. So it's really hard to miss your satellite with that. You could be pointing a little bit the wrong way and you would still get a signal, and the same goes the other way. The satellite could be pointing wrong a little bit and you would still get a signal. The downside is that it's very expensive. You need really big facilities like 40-foot satellite dishes, and they're really expensive to maintain. And the data rates you get are limited. Think of your fastest home fiber internet, like 1 gigabit a second. That's really where things top out. And it is never going to be faster than that, which is not enough. For example, there is a brand new NASA satellite called NISAR that is a radar imaging satellite, and it will collect 35 petabyte of data every year.
Wow, it's a lot of data.
Yeah, which I was told that is about as much data as all previous NASA Earth observation satellites have collected over all of their combined lifetimes.
So how are they going to get it back to Earth?
Yeah, right. But with one of these state-of-the-art facilities that are very expensive. It costs tens of millions of dollars every year just to get the data back. Yeah. So that's where the laser come in for the future. You can get much higher data rates. There are plans in the works for standards and facilities that can do 1 terabit per second. So that's 1,000 fiber connections.
Wow.
Up to the satellite.
But the tough part is you don't have that cone. Right?
Exactly.
You have to point the laser right at the satellite.
Exactly. So radio waves and visible or near infrared light are both part of the electromagnetic spectrum, but different wavelengths. So the length of one oscillation of this wave for radio frequency could be centimeters to a few meters even. For light, it is about 1 micrometer, so tiny. And what that does is that beam that we generate with a laser, for example, stays very tight and focused all the way. So instead of having to point within a few degrees accuracy, we have to point within 1,000th of a degree all the time and track those satellites very accurately.
So that's difficult, but the consequence is you can get much higher data rates.
you can get much higher data rate. And it turns out even with all the difficulty, it is still lower cost to build an optical ground station than it is to build a high frequency radio ground station.
Yeah. Now, I know you're not building all of this by yourself. You have students involved in much of your work. In fact, I know you have graduate students and undergraduates who are all involved. Tell me about your involvement of students in this work.
Yeah. So right now, in working in this group, we have 3 undergraduates who are working towards their capstones in physics. We have 4 PhD students in the physics program, and we have 1 master's student and a postdoc. So the group is growing. And so they're all contributing in different ways. For example, we have 1 undergraduate student who is writing a site report about what the optical properties of our atmosphere are. One of the things that makes it hard to use lasers to talk to satellites is that the atmosphere is turbulent. Think of if you're looking on the surface of hot pavement in the summer, you see the air kind of flickering. The same thing always happens to the atmosphere, just not that strong. That's why we don't see it. But the atmosphere is 100 miles thick. So there's always something going on, and that distorts the laser beams. So we have instruments that measure these site conditions, and we have a student doing the data evaluation and writing a report on that. And we have one of the PhD students writing code right now to track satellites and acquire signals, and so that we can tell potential operators of spacecraft how much satellite time they could expect here, depending on the orbits of their satellites.
That's really cool.
Yeah.
That's really cool. And I know that there's been a lot written about the work that you're doing. Where can our viewers actually find out more about this work, this amazing work that you're doing?
There's a lot of information already out there, and more and more coming. So we had that wonderful article in und today about this facility that we're building. You can always get in touch with me and find me through the directory. And we also have a website about the facility that lists some of the capabilities on the website for the College of Arts and Sciences. But especially for undergraduate students, we'll have more opportunities coming up. We'll be hosting senior design projects for the engineering departments. We have collaborators in aerospace and engineering that want to get students involved. And of course, there's the easiest way, which is to join the physics program.
There we go, right. Sign up for the physics major.
Right, it's as easy as that.
Easy as that. Well, Professor Markus Allgaier, thank you so much for being with us today. And great topic. And if people are walking by Witmer Hall, they can look up on the roof and see something.
Absolutely.
And that's your equipment.
Yep, that's the new big telescope.
The new big telescope. So when you think of the telescope or you see it, think of Professor Allgaier. And it's great that you tuned in today. Thank you for joining us. And all of the references that Markus just talked about will be included in the transcript of today's video. So you can look there to get the actual links. Thanks everybody for tuning in, and thanks to Markus.